In this section, we will study about the Laplace transform of several common functions. The first one is a constant function. Constant function is given like that. It's a constant over whole time. So taking integration minus infinity to infinity and the basis function like that. By taking integration, it gives minus k times s over e to the minus st, and integration range changing from minus infinity to infinity. Then if we apply t to infinity or minus infinity, the first apply infinity to here, there is a typo. This should be minus k over s. That's the spot. Minus k and s is given here. And by applying infinity to here, s times minus infinity. And the minus infinity will give these expressions. And here, we need to think about the reason of convergence. There is no such a reason of convergence that exists in these cases. If sigma is positive, then this goes to the divergence. If sigma is negative, this term goes to the infinity. So XS doesn't have a reason of convergence. It didn't converging. Okay. And the second one, unit impulse cases. By definition, unit impulse is only non-zero t equals 0, except t equals 0. Okay, all times is 0 except t equals 0. So just replace t equals 0 at here, then it will give 1. And this one is actually finite duration signal. So reason of convergence is the whole S-plane. The next one is a unit step function. Unit step is defined from 0 to the infinity, right side signal. So by taking the integration of this one, it will give this way. Minus st. And we need to integration variable changing from to the 0 to the infinity. So when we insert the time with the infinity, it should be vanished out. So to satisfy that one, this condition should be satisfied. It means that the sigma should be positive. Then e to the minus sigma t, as t goes to the infinity, it goes to the 0. So it is 1 over s. Reasonable convergence is this one, positive right-sided. And rectangular pulse is a finite duration one. You know that this rectangular signal looks like this way. This is tau over 2 minus tau over 2. Magnitude is 1. So we take the Laplace transform of this one. So by taking the integration this one over this time period, it will give this result. And if you give tau over 2 to the t, then it will give this value, and the minus tau over 2 will give positive value. So it will give, in this case, this will come out. If you enter this one, this will come out, and s is remained here. But you know what, that e to the alpha minus e to the minus alpha r divided by 2 will give sine hyperbolic functions. Okay, and e to the alpha plus alpha over 2 will give cosine hyperbolic alpha. So hyperbolic functions are defined this way. So by use of that result, we can define this one is sine hyperbolic s tau over 2 and remain s. In this case, the region of convergence is the whole area of S, because it's a finite duration, and the finite number, the absolute integral signal of this one means it has area is tau. Okay, so absolute value of x tau d tau minus tau over 2 and the tau over 2, because this one is a finite duration, it's a finite value. So if it's satisfied, then the whole S-plane becomes the region of convergence. Next, exponential function, we already studied about this one. This one is a right-sided signal, and take the Laplace transform starting from 0 to the infinity. it will give 1 over s plus a, and the region of convergence are defined by this property. So to satisfy these conditions, real part of s should be greater than the minus a. It means that in this case the pole is located minus a. So region of convergence should be defined right side of this value. So this part is the region of convergence. Okay. The next topic, let's think about the inverse Laplace transform. And when we take the inverse Laplace transform, we need to consider region of convergence. Firstly, let's look at the Laplace transform of this one. Laplace transform xs defined 1 over s times s plus 1 s times s plus 2, like that. We need to partial fraction expansion. Partial fraction decomposition gives these expressions. Okay, we have the Laplace transform of this one. You know what? This one is exponential, this one is a unit step. You can compare that result, this one, and also you can compare the unit step function. So you can think about this one related to unit step. These two things are exponential functions, but we need to know the region of convergence to find out the inverse Laplace transform of xs. Let's consider first case. The first case, the region of convergence are defined at these regions. Sigma is positive, so obviously in this case this one is right-sided. Okay. Right-sided signal. So xt is defined after t equal positive cases. So in this case, the rightmost pole is this one. So the right side of that one. So all these three components is right-sided signals. So get this area satisfied. Sigma is greater than 0. That's this pole, and this pole is minus 1. Greater than this one, and also greater than minus 2. So the region of convergence is greater than all the poles. So all signals should be interpreted as right-sided signals. So it can be taking inverse Laplace transform by use of that one. This one is a unit step function. That's this one. And this one is 2 times e to the minus t times ut. Unit step. Right-sided signals. Now, so that's this part. And this one e to the minus 2t times tau. So right-side signals is this one. What about the left-sided signals? You know that this is a leftmost pole. Everything is the left side. So region of convergence is less than minus 2 and also less than minus 1 and less than 0. So all signals is left-sided one. We need to interpret this one left-sided one. When we consider left-sided, we need to consider minus and u minus t. Okay. So this part, we already talked about that property for the previous example. Okay, here. Left-sided cases, we introduce these two things. Left-sided signal, this should be negative. Sorry, this is another typo. Okay. This way. And the right-sided signal example are shown here. So this one is a right-sided signal. The Laplace transform is defined in that way. Region of convergence are right-sided. Left-sided one is minus and minus ut. If you're taking minus and minus ut, that gives the same expression for the Laplace transform. Look at here, the right-sided and left-sided Laplace transform pattern is the same due to this minus and minus ut, and the region of convergence is different. Okay. So by use of that, we can interpret the inverse Laplace transform of this one. When we take the inverse Laplace transform based on this second region of convergence, all signal is left-sided. All signal is left-sided. Left-sided means the minus should be come out. That's this part, and minus ut should be multiplied. This one is a left-sided one, and interpret this one is a unit step, and this one is exponential, and this one is another exponential function like that. This is all signals are left-sided one. The third one, at this moment, the region of convergence is in between minus 2 and minus 1. In this case, we need to interpret the region of convergence. Region of convergence is larger than -2. So, what does that mean? This one is a right-sided signal, so you need to think about this one is a right-sided signal. Pole is -2, okay? And another 2 pole, this is less than -1, and also left side of 0. So in these two signals, it's a left-sided signals. So these two things should be interpreted as a left-sided. So that is shown here. So xt can be given the unit step 1 over s should be interpreted as a left-sided one. Left-sided means a minus and minus ut. So here is -1.5, that's this one, and 1 times minus ut. Okay, this one is a left-sided 1 over s. And the left-sided -2 over s plus 1 is an exponential function, but it is left-sided one. So it is -2 times e to the minus t, and it is left-sided signals. So front two Laplace transform interpreted as a left-sided signal, but the last one is a right-sided signal. So 1.5 times exponential in the right-hand side. So this is two-sided signals. Last one, region of convergence are defined in between -1 and 0. We need to interpret region of convergence. This region of convergence can be interpreted greater than -2 and -1. So in these two signal cases, this one is a right-sided one, and this one is less than 0. So this is a left-sided one. So -1, -2 is a right-sided. In this case, this signal can be interpreted, these two poles is right-sided because of this one. Region of convergence located the right side of these poles, and this one is left-sided. We need to interpret this one as a left-sided one, so that's why it is -1.5 and minus ut. That's the left-sided one. The other two is a 1.5 times -1.5. It will give 1 over e to the minus t times ut is omitted. Ut should be multiplied here, and the last one is 1.5 e to the minus t and ut should be added here. So I would like to rewrite this one here. Xt is -1.5 ut. Okay, and 1.5 minus 2, that gives minus e to the minus t ut. This one is a right-sided, and the last one is a 1.5 half times e to the minus st, 2 times st, 2 times t, sorry, 2 times t and ut. So from here, the first one is left-sided signal, but last two is right-sided signals. So you can interpret the Laplace transform based on the region of convergence. And the last one is just to explain the inverse Laplace transform. We know that this one is an inverse Laplace transform.